Hello, Math 2. This is Mrs. Bricky, and this video is for Unit 9, Lesson 4. We're going to be talking about the graphs of quadratic equations or quadratic functions with non-real zeros. So first of all, just want to talk about how the zeros of a function show up or relate to the graph of a function. So recall that the zeros of a quadratic equation correspond with the x-intercept of the related function's graph. So for example, if we have x squared plus 4x minus 21 equals 0, for this one I chose a factorable. For this example, I chose a factorable quadratic. Just to save us a little time. So thinking about factoring x squared plus 4x minus 21, we know that each of the factors is going to lead with an x in this case. We're thinking about the number 21. 21 is 1 times 21. Whoops, that looks like a 7. 1 times 21 or 3 times 7. And our middle term here is a positive 4x. So our factors are going to be x minus 3 and x plus 7. So the two solutions are positive 3 and negative 7. And remember, those solutions come from setting each factor equal to 0 and solving, but we usually kind of do this step in our head because we can. So if x minus 3 is equal to 0, then that means x is equal to 3. And if x plus 7 is equal to 0, that means x is equal to negative 7. So the solutions to this equation right here correspond with the x-intercepts on the graph of that related function. So if our function is x squared plus 4x minus 21, we see x-intercepts at negative 7 and positive 3. So what would it mean for the function if a quadratic equation had two non-real solutions? What would the x-intercepts of the graph of a function with non-real zeros be? And that's kind of what we're going to look at and think about today. So we're going to start with vertex form for a second. So I've got three equations here. X minus 5 squared is equal to 0, x minus 5 squared minus 4 is equal to 0, and x minus 5 squared plus 5 is equal to 0. We're going to sketch each of these related functions, and then on the next slide, we're going to solve those three equations for x. So this is going to be a good practice for us of graphing vertex form of a parabola again. So remember that if we have a function in vertex form, y equals a multiplied by x minus h squared plus k, the h and the k here give us our vertex of the parabola, and the stretch factor a is that. That's what we'll graph using that 1, 3, 5 pattern. So these parabolas all have a stretch factor of 1, which means they are just going to follow a 1, 3, 5 pattern. So the vertex of this first parabola, f of x, is 5, 0. So that's right here. And we'll go up 1 over 1, up 3 over 1, up 5 over 1. And we've got those two symmetric sides. Oh, geez. My parabola graphs are not that great today. Sorry. So that's our first function, f. For function g, our vertex is at 5, negative 4. So here we go. There's our vertex. Up 1 over 1, up 3 over 1, up 1, 2, 3, 4, 5 over 1. 1, 3, 5. So we get this green parabola for function g. And for our last parabola, h of x, it has a vertex of 5, 4. And that's right here, up 1, up 3. Oh, it just barely fits. Okay, so we just drew our three graphs. So let's think about the x-intercepts of each of these for just a second. For function f, it just has that one x-intercept right there at 5. For g of x, it has two x-intercepts. The x-intercepts are at 3 and 7. And function h has no x-intercepts. There's not any. It does not cross the x-axis. So let's solve the related functions and see what their solutions are. So here are our three equations. X minus 5 squared equals 0 is our first. So we're going to take the square root of both sides. We get our plus or minus symbol there. So that leaves us on the left with an x minus 5 equals, and this is a positive negative root 0, but the square root of 0 is 0, and 0, I mean, it's not really positive or negative. It doesn't have a sign, so we don't really need our plus or minus symbol because it's just 0. So our last step is that we want to add 5 to both sides of our equation, and we get x equals 5. We just got one answer, which is interesting. We'll talk about that in just a second. Next equation, x minus 5 squared minus 4 is equal to 0. So we need to start by adding 4 to both sides of our equation. So that leaves us with x minus 5 squared is equal to 4. We can root both sides of that equation, positive and negative. So we get x minus 5 is equal to positive and negative 2. And our last, well, sort of last step would be to add 5 to both sides. So we get x is equal to 5 plus or minus 2. Well, 5 plus 2 is 7, and 5 minus 2 is 3. So we get x is equal to 7 and 3. And our last equation, we're going to start by subtracting 4 to get that square by itself. So we get x minus 5 squared equals negative 4. We want to root both sides of our equation now, plus and minus. And that leaves us with x minus 5 on the left. And on the right, we have positive and negative. Well, this is the root of a negative number, so it's imaginary. Positive and negative 2i. And our last step is to add 5 to both sides. That real 5 can't combine with that imaginary 2i. So we have 5 plus or minus 2i as our two answers. So I want to look back at our graph and think about what it means for the graph if our quadratic equation has non-real zeros. So my first function was x minus 5 squared, and that is the blue function. And you can see that the solution we came up with was just one value, 5. This is the one case where quadratic will only have one answer. It's kind of, it's called, we'll talk about it in a second, but it is called a multiplicity or a repeated root. You could think of it as 5 plus and minus 0, but 5 plus 0 and 5 minus 0 have exactly the same value, which is 5. So our two answers are just the same. It's like a 5 is the answer twice to that equation. Our second equation, x minus 5 squared minus 4 is equal to 0. That corresponds to that green parabola, and you can see that our two solutions are those two x-intercepts. And our third parabola, our purple parabola, corresponds with this third equation. And so what it means when a quadratic equation has non-real roots, it means that the related function will not have any x-intercepts. The related function does not have any x-intercepts. The solution, the equation, does still have two solutions, but the graph will not have any x-intercepts. The function will not cross the x-axis. Sometimes I call these floaters. So either they're floating up above the x-axis, or if they're reflected, then they sort of are reflected and below the x-axis, but they will not cross the x-axis. Okay, so it seems like that equation, and we talked about this a teeny bit, we'll talk about it a teeny bit more. It seems like the equation x minus 5 squared equals 0 has only one solution. And I keep telling you over and over again, all quadratic equations have two solutions. And it is true that all quadratics have two solutions, but there are quadratic equations that have the same solution twice. And when that happens, we call it a repeated root. For example, let's solve these two equations, and we're just going to use factoring here. You could use the quadratic formula if you weren't finding a factorization that works, but these two are both factorable. So if I factor this, I'm thinking about and focusing on that 36 at the end. 36 has several ways of we have several ways to get a product of 36. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. So there's 5 different possibilities. Our quadratic that we are factoring has a middle term of negative 12x. So we are going to choose those 6's, both negative. And that works with our positive 36. We can get a positive 36 if we multiply a negative 6 by a negative 6. So if we look at our two factors to get our two answers, it's 6 and 6. They're the same. When it's the same number for both of the answers, you don't have to list it twice. You can just say x equals 6. Now, please note, this is different than the quadratic x squared minus 36 equals 0. That one factors as x plus 6 and x minus 6 with a 0 middle term where we have a positive and negative 6. This is different than that. The one we are working on is much different than that. Our two factors are both x minus 6. They have the same sign in there. So the two answers are just positive 6. And so you can just list it once. And it is okay to say that this quadratic just has one real solution. But because it's quadratic, we know that if it just has one solution, it has to be a repeated solution. So let's factor this one again just for another practice. X and x at the beginning of each factor. 1 is our number at the end. There's really only way to get a product of 1. It's 1 times 1. So since this is a positive 2x in the middle, we know each of those factors is going to have a positive 1 in it. So then our two solutions are each negative 1. So we would say that this quadratic just has one real root, one real 0, and it is the x value negative 1. Okay. Using all of your amazing knowledge of quadratics, match each function with its graph. Well, the first thing I would notice if I was doing this myself on my paper is that 3 of them open downward and 3 of them open upward. So I am going to focus first. And again, if you have forgotten how to tell that, these ones are a negative in front, so they open downward. Okay, one thing to notice is that several of these have x-intercepts, and a couple of them do not. So I have a downward function that has 2 x-intercepts and one that has a 1 x-intercept. I've got, and then the C has none, D has 1, E has 2, F has none. Let's focus on these upward ones first, since our upward equations come first, and then we'll look at the downward equations. Okay, so we can try to factor these if we would like to. So I'm going to start with number 1. If I factor it, it's an x multiplied by an x minus 2. Now, sometimes we forget to look for a common factor, but this one just has a common factor of x. So since it has those two factors, we know that we have two x-intercepts. The x-intercepts of this graph are at 0 and 2, and it opens upward. So that has to be graph E. So E goes with equation 1. Equation 2, we can factor x and x. The factors of 1 are 1 and 1, and it's a negative 2, so we have x minus 1 times x minus 1. That means it has an x-intercept of positive 1. It's a repeated root. That means it is graph D. So 2 goes with D. Number 3, x squared minus 2x plus 2. That has to go with F. It's the only one left that opens upward. And it is, you could also think of this as being shifted 2 units up from the equation for graph E. So think about if you shifted this 2 units up, it would be a vertex right there at 1, 1. So that is graph F. So there's a lot of ways you can kind of think through these. All of those ways of thinking about quadratics and how, if you can be really fluid about how you think about these, that's really awesome. Okay, the other 3 graphs open downward. So I'm going to start with number 4 and factor out a negative x. If I factor out a negative x, that leaves an x minus 2. So this is a parabola that opens downward and has intercepts at 0 and 2. So this is graph A. We can think of number 5 if you want. The only difference between number 4 and number 5 is this minus 1. That means it has to be shifted down from that previous graph. So this is definitely B. And then finally, this one's shifted down 2 from graph A. And so that would be graph C. So there's a lot of ways you could match these up. Another thing that you could use to match them up is their y-intercepts. There's tons of ways to do this. Okay. We're going to think a little bit about these graphs a little bit more, and then we'll finish up circling back to projectile motion. So function f is x squared plus 14x plus 44, and you can see the graph there of function f. And function f corresponds to this equation, x squared plus 14x plus 14 equals 0. That's going to tell me about these x-intercepts. So what sort of solutions does this equation have? I know that it has real solutions. They look like they're probably irrational solutions, like maybe with a square root in them, but they could be fraction or decimal values is another way that they might show up. We could find out for sure if we did solve that equation, but I know they are real numbers because I can see the x-intercepts. Function g is also shown on this graph. It has the equation x squared plus 14x plus 54. What sort of solutions does that equation have? X squared plus 14x plus 54 equals 0. I know that this one has non-real solutions. And I know that because there are no x-intercepts on that graph. So my question is, for what value of c will x squared plus 14x plus c equals 0 have exactly one real solution? Well, if it has one real solution, that means I want that vertex to be right on the x-axis. And so that means it needs to look approximately like this. And so we are trying to figure out what the c value is. Well, the c value for our first graph is 44. I'm going to kind of write that on the side. C value is 44. That corresponds with the y-intercept, but we can't really see our y-intercept on this graph. And the green graph corresponds with a c value of 54. And if you look at the vertex or the vertices of these two, this one has a vertex at -5. This one has a vertex, a minimum value of +5. We want something halfway in between that, and that will land it right on the x-intercept. So in this case, we want our C value to be 49. We want our C value to be 49. That's halfway between 44 and 54. And that's going to put that vertex right on the x-axis. So here's another one, and we don't have a graph to look at. For what values of C does x squared minus 8x plus C equals 0 have two real solutions, one real solution, and two non-real solutions? Thinking about having one real solution, we have to have that vertex right on the x-axis. So let's see, 1, 2, 3, 4. So our axis of symmetry is at -b over 2a. So for this one, that's 8 over 2, and that's +4. 1, 2, 3, 4. Okay, so we want to find a parabola that has its vertex right here. That would have one real solution. So if we have a vertex right there, that means that our one way of doing this would just be to think about that means one version of the equation of this is x minus 4 squared. Well, that's the same as x minus 4 times x minus 4, and that's x squared plus, x squared minus 4x minus 4x, x squared minus 4x plus 16. So that would be a C value of 16. So if I wanted a parabola that has two real solutions, then any shift down from there is going to have two real solutions. So for two real solutions, I just need a C value. To shift this down means I would subtract numbers. If I subtract 1, it's going to be 1 below. If I subtract 2, it's going to be 2 below. So it just has to be, C would have to be a number that is less than 16. For example, if it was x squared minus 4x plus 15, that would be below this parabola. And for non-real solutions, I would just need to shift this parabola up. So I would just need to add numbers to that ending number. So that means that C would have to be greater than 16 for non-real solutions. Okay, I'm not going to do that second part for the video. Okay, our last example, we have a juggler throwing a ball into the air. The ball leaves the juggler's hand 4 feet above the ground and has an initial velocity of 30 feet per second. So here is our equation. H equals -16t squared plus 30t plus 4. So you can see the gravitational constant first with our t squared. We've got our initial velocity with the t, and we have our initial height at the end. Okay, so this is modeling the height of the ball at time t. Our first question is, does the ball reach a height of 25 feet? So as he's juggling, does the ball ever go 25 feet high? So this is an h value. 25 feet is an h value. So I'm going to put it into the equation for h. 25 equals -16t squared plus 30t plus 4. And let's just solve this equation. If we can find a time that this equation is true for, then we will know that it hits that height. So we're going to start by subtracting 25 because we want our quadratic to be equal to 0 so that we can apply the quadratic formula. 16t squared plus 30t minus 21. Now you could, if you wanted to, you could try to factor it, but with these sorts of coefficients, usually when I'm working with projectile motion, I just use the quadratic formula. Whoops, our variable is t instead of x. So t equals, quadratic formula is -b plus or minus the square root of b squared minus 4 times our a value multiplied by our c value, all divided by 2 times our a value. Okay, so this is negative 30 plus or minus the square root of something over negative 32. And if you calculate this number in your calculator, don't put the root in case it's negative, but that would be a negative 444. And I don't even need to keep going because this is a negative square root. This is an imaginary number, which means, whoops, I did not spell imaginary right. This is an imaginary, complex, non-real answer. That means that the ball will never reach a height of 25 feet. So no, it does not reach a height of 25 feet. So now let's answer this second question. The second question or the second part says, does the ball reach a height of 10 feet? So again, that's an h value. So we'll put it in the equation for h. 10 equals negative 16t squared plus 30t plus 4. And we will subtract 10 to get our 0. So we have 0 equals negative 16t squared plus 30t minus 6. So in the quadratic formula, this becomes, and really the only difference here is that c value. So our quadratic formula looks very similar. Negative 30 plus or minus the square root of 30 squared minus 4 times our a value times by our c value, and that's all over 2 times our a value. Okay, so let's figure out the inside of that root. Oh, whoops, I'm sorry. My denominator should be negative 32 because it's 2 times negative 16. That root is 516. And since that's a real number, that means the ball does reach that height of 10 feet. And it actually reaches that height twice. Negative 30 minus root 516 divided by negative 32 will give us one of our answers, and negative 30 plus root 516 divided by negative 32 will give us our second answer. So the ball hits that height at 0.28 seconds and at 1.65 seconds. And sometimes my tablet does not work right. So that makes sense if you think about, throwing a ball up. The ball is reaching that height of 10 feet on the way up, and then it's reaching that height of 10 feet again on the way down. Oh no, I thought I had a graph of this, but I don't. So in this case, our ball is starting about 4 feet high. Here's 10, way up here is 25. The ball is going up and down, and it does hit that height of 10 feet twice, but it never gets as high as 25 feet. So doing the quadratic formula like this and looking for non-real roots can help you figure out whether or not a projectile, like a ball or something that you're throwing, hits a certain height. All right, so today's big idea was just that quadratic functions that have non-real zeros do not cross the x-axis. If you know the vertex of a quadratic function and the direction it opens, you can determine the number and type of roots that its related equation has. So let me or your teacher know if you have any questions on this section. And next time in class, coming up real soon, we will be reviewing and taking a test on this unit. Thank you.